If the background, theory, prior evidence, prior research findings warrant it, a researcher may begin an experiment with a specific prediction about the direction of the treatment effect. We always start out with a null hypothesis, but depending on these other factors, we may choose to supplement the null hypothesis with an alternative or research hypothesis. So in effect, what we are saying is, first of all, nothing is going to happen. The treatment is not going to have an effect. However, if the treatment does have an effect, we're going to predict that the effect will be in terms of increased scores, a higher mean value, or decreased scores, a lower mean value. Thus, if we supplement the null hypothesis with an alternative research hypothesis, we will be conducting a directional one-tailed test. Directional because we are predicting either a mean value less than the population mean or a mean value larger than the population mean. Figure 8.7 on page 225 in your book shows the bell curve with the boundary to the critical region consolidated into one tail on the positive side of the distribution. A directional one-tailed test requires two changes in the step-by-step hypothesis testing procedure. One, in the first step of the hypothesis test, the directional prediction is incorporated into the statement of the hypothesis. And two, in the second step of the process, the critical region is located entirely in one tail of the distribution. After these two changes, the remainder of a one-tailed test proceeds exactly the same as a regular two-tailed test. Because of this consolidation, the critical z-values that you will use in step 2 of the 4-step hypothesis testing process will be different. To locate these values, you first find the value closest to 0.0500 in column C, the tail column, in the z-score table in your text. When you get there, you'll have a familiar dilemma because you have two proportions that are equal in distance from 0.0500, 0.0495 and 0.0505. Remember what to do? You will select the value that is associated with the larger z-score, which is 1.65, just as it is shown on the slide. Take a moment now to locate the critical z-score value that will form the boundary to a one-tailed test when you're using an alpha of 0.01. All researchers agree that one-tailed tests are different from two-tailed tests. However, there are several ways to interpret the difference. One group of researchers contends that a two-tailed test is more rigorous and therefore more convincing than a one-tailed test. Remember that the two-tailed test demands more evidence to reject the null hypothesis and thus provides a stronger demonstration that a treatment effect has occurred. Other researchers feel that one-tailed tests are preferred because they're more sensitive. That is, a relatively small treatment effect may be significant with a one-tailed test, but fail to reach significance with a two-tailed test. Also, there is the argument that one-tailed tests are more precise because they test hypotheses about a specific directional effect instead of an indefinite hypothesis about a general effect. In general, two-tailed tests should be used in research situations when there is no strong directional expectation or when there are two competing predictions. For example, a two-tailed test would be appropriate for a study in which one theory predicts an increase in scores, but another theory predicts a decrease. One-tailed tests should be used only in situations where the directional prediction is made before the research is conducted, and there's a strong justification for making the directional prediction. In particular, you should never use a one-tailed test as a second attempt to salvage a significant result from a research study for which the analysis with a two-tailed test failed to reach significance.